Okay, so here I am going to explain some topics from module 3. Okay, so module 3 is actually went to two chapters. One is about Poisson's and Laplace equation, the other one is on steady magnetic fields. We'll be seeing only the first half chapter of this module 3, that is Poisson's and Laplace equation here. So there are two derivations in this particular chapter and the rest are all problems. So the first derivation is on the derivation of Poisson's and Laplace's equation. Okay, so here these two important equations are there. We're going to derive it and then we're going to use the derived result for solving problems, right? So the first one is to derive the equation for Poisson's equation, and from there we'll get the Laplace equation. So to start with, we have already learned about Gauss law in point form in module 2. Okay, the Gauss law in point form is given as del dot D equal to rho V. Del is nothing but the divergence operator. This is the flux density and this is volume charge density. Okay, so del dot D is equal to rho V. This is the Gauss law in point form. And we also know that the flux density and electric field intensity E are related using this equation. That is D is equal to epsilon into E. So what we are going to do now is we are going to substitute D as epsilon E in this first equation. So by doing that, we are going to get del dot epsilon E, which is equal to rho V. So in place of D, we have just put epsilon into E here, right? Then now we are going to do one more substitution, and that substitution is called as gradient equation. Okay, we'll be learning about this gradient equation in module 2. Okay, this gives you the relation between electric field intensity and electric potential. Okay, so V here stands for electric potential. Okay, and the relation between these two is that it is equal to E is equal to minus del V. E is equal to minus del V. It is the variation in potential. Intensity is equal to variation in potential. It's a decreasing quantity. Okay, so that's why you have a negative sign here. So now what I'm going to do is I'm going to substitute E in this equation as minus del V. So I will be getting del dot epsilon into, instead of E I'm going to put minus del V here. Okay, now I can take this minus and epsilon outside because they are constant. Epsilon is constant, so I can write it as minus epsilon. The remaining part will be del dot del V, which is equal to rho V, right? So now I'll keep this del dot del V here and take this minus epsilon to the other side. It becomes minus rho V by epsilon. And now we also know that if I'm taking dot product of two similar vectors, then the answer is always going to be the magnitude square of it, right? Actually, dot product equation is magnitude of the first one into magnitude of second one into cos of the angle. If you have same vectors, then the angle will be 0 degree because they are parallel, right? You will be having the vectors like this. The vectors are on top of each other because they are same vectors. A bar, it's on top of each other. They are same vectors. So the angle is obviously equal to 0. And the answer is going to be magnitude square. Similarly, here you have del dot del. So del dot del will give you del square V. That's equal to minus rho V by epsilon. And this is your Poisson's equation. This is called as Poisson's equation. Okay, so this is the derivation for Poisson's equation. So we started with Gauss law in point form, that is del dot D equal to rho V equation. In this we replaced D by epsilon E, and we again replaced E by minus del V. So two substitutions were there, two replacements were there. And this, then we have just rearranged the terms. We are going to get del dot del here, which is nothing but del square. So this del square V equal to minus rho V by epsilon is the Poisson's equation. Now in the same derivation, in the next step, if I assume a region, a certain region where we say that there is no charge inside that region. Okay, so I'm considering a charge-free region, which implies that the charge inside this region is 0. If the charge is 0, then the volume charge density, which is Q by volume, is also 0. So if this is the case, then what happens to the Poisson's equation? It becomes del square V equal to 0. Okay, and this equation is called as Laplace equation. Right? So in the same Poisson's equation, if I assume that there is a region, certain region where there is no charge inside that, then the equation can be simplified to del square V equal to 0. And this del square V equal to 0 is called as the Laplace's equation. It's a special case of your Poisson's equation. Okay, so Laplace equation is special case of Poisson's equation. We can get Laplace from Poisson by making this rho v equal to 0. Okay, the assumption is that the uh, region does not have any charge inside that. Okay, so this is the derivation for Poisson's and Laplace equations. In the next video, I'll be explaining some problems based on this. Okay, you have different coordinate systems, right? Cartesian, cylindrical, and spherical. The del square V equation is different for the three coordinate systems. So based on that, we have to solve some problems for different types of systems. So we'll see that in the next video.